then we have to write down the equilibrium equation for the body. There are different approaches that are being used. So earlier we talked about writing down the equilibrium equations in terms of summation of fx is equals to 0, m equals to 0 about the given x. Now there exists another kind of principle which is called principle of virtual work, which can be used to find the equilibrium position of a. So what is this virtual work principle? In this particular principle, you have many forces which are acting on the body. Corresponding to those forces, along the line of action of those forces, and you assume there is some kind of virtual displacement. So the virtual work can be defined by the virtual work, virtual displacement into the force, which is. Now the important thing is that those forces should be external. So this principle says that under the action of external forces, force let's say F, and external moment M, the virtual work done is defined as EW, which is F into delta U plus M into delta theta. So this is your virtual. So basically this should be dot dot. So this dot product of these two. So delta W is your virtual displacement, and delta theta is your virtual rotation, angular displacement. Just remember that these F and M are external forces and movement. So under this principle say that under the influence of these external forces and movement, under the equilibrium, this work done becomes 0. It means that F dot delta U plus M dot delta theta equals to. Now let us try to see how it really works. Let us say there is an object like this, and this is again up, and this is connected to another. Okay. Now, if you are if you have to find out the force P required for the disturbance. Now, let us say this is the block where you are applying moment M. The force E that you are applying at this particular place, and there is another load F which is applied at this location. Let us assume that the length of these elements are L and this angle is that now solve this problem using virtual law. If you have to apply the principle of virtual law, theta, this is your actual position. So let's call this as A, and the forces which are acting like that, their movement and when it moves down and it rotates in this direction, what will be the virtual position of this point? That the position of this virtual object somewhere there. So what has to be done? Corresponding to all the external forces and movement, you will have to take the corresponding displacement. It means that corresponding to this M, you have here delta theta. Corresponding to this particular thing, corresponding to this F, you are having displacement of delta Y. Corresponding to P, you have a displacement of delta X. Now you have to find out delta Y, delta theta and delta X in terms of like at least one point. But before that, let us apply the principle of virtual. Principle of virtual work says that when times delta theta, since the direction of M and theta is same, so dot product of both of them will be positive. So this can be written as M. Now in a similar way, the displacement of this B is in this direction and F is also acting in the same direction. So again this will be positive, which is F into delta Y. Now P, direction of displacement is this, but P is acting in the opposite direction. So the virtual work will be minus P times delta X, and total under the equilibrium condition, the total work done should be equal. Okay, this is how the principle of virtual work. But how you will find out the equilibrium of the forces? To do that, what you really have to do is you will have to find out the relationship between delta X, delta Y, and delta theta. Let us try to do that using this. So you can see that this total is your L, total is your L, okay, and this is your X and this is your Y. So if you want to correlate this thing for a given theta, this is your theta. So in this particular case, you see that your L is, sorry, for given delta theta or theta, let us say, for given theta, your X is given by this plus this. What is this? This is L cos theta. This is L cos theta plus L cos theta. So total X of this particular point. This X. So X is L plus L. So this leads to L cos theta. Okay. Now when you try to find dx, this is nothing but minus 2L sin theta. Okay. So here 2L cos sine theta and d theta. In a similar way, you can find out what is the position of y in terms of theta. So y will be given by L sine theta, and if you find out this dy, that will be L cos theta. Now you can see that you can write dx in terms of d theta, dy in terms of d theta, and you are getting. So now the important thing is that when we wrote this particular thing, either you can assume the direction as it is, either you can assume the direction as it is, or you can just write the summation of all that. So I will just see how your m and theta is really varying. So this is your theta basically, and this is your now the application of m, which is in the opposite direction, and theta positive is in this direction. So in this case, what we wrote was when d theta is the positive and m is also in the same direction, then it is positive. However, it turns out that if we take this as a theta and this is your del theta, so application of m is reducing this. That this should be negative and positive. Okay, so if you try to use this particular concept, so what you will end up over here is minus, so delta w is equal to 0, principle of virtual work principle. So this will give you m delta theta. Now f and delta y are both same, so this will be plus f. What is dy? Dy is your L cos theta delta theta, and what is your last one is p and dx, both are in the opposite, so that will be negative. That will be p 2L sine theta and delta theta, all of equals to 0. If you take this common, what you are going to get is minus m plus f L cos theta minus p L sine theta, okay, into L theta, all should be equals to 0. Since L theta can't be 0, to have the equilibrium, what is required is your m should be equals to FL cos theta minus 2PL sin theta. If the question says that you have to find P to bring things under equilibrium, then in that case you should be having FL cos theta minus m divided by 2L sin theta, the force that are required to put things under equilibrium. So this is a very good example of understanding. So you can understand the principle of virtual work. Let me the principle of virtual work. So let me again give you another example so which this principle is more clear. Let us take an example, second example, in which you are having, let us say, a fixed portion. Here the spring is there which is connected to a roller. Okay, and here again you are having two, is a force P, right, and what is given here is this L and L. Here there is no friction. K is given and H is the unstretched length of the spring. And let us say this is your or let me not your theta and this is your theta. Now solve this problem using the principle of virtual work. What you have to find is find theta under equilibrium condition, and also find the tension in the spring. So what you have to do, first we have to find out, if we have to apply the principle of virtual work, we will have to first find out all these things like external forces. So what are the external forces? At the moment only one external force exists, which is have another external force. Let us take out this point and also this particular point, K. Drawing the FBT of a system. Yes. So we are removing this particular surface and also a spring. So what will happen? There will be S, which is nothing but A. So let us assume that this is the position of your equilibrium X, and unstressed part of your spring was H, which is given here. Okay. So it means that the stressed part is simply S. Okay. So your force Fs over here will be given by K times S. K is your spring constant which is given, and S your displacement. So, and there is also one load which is acting as normal. And now let us see, and where is another one? This is the actual external force which was acting. Now if we take out this particular thing, there are three external loads. One is your P, another one is your Fs, and third one is your N. So external forces are E, Fs, and N. What are the corresponding displacement? So let us say your displacement of this particular point is delta, and displacement of delta x. Displacement of this particular point is delta y. It means that eventually we are assuming this one as y and this position is. Now we have to find out if this is your theta, what is your x and y. So let us assume the displacement along P is your delta y, the displacement along Fs is delta x, and displacement along N, since there is no displacement but this point is moving in this direction, so here again del x, and the angle between them. So if you see the angle between these two, so P is the direction of dy, so angle is equal to 0 degree. Fs is in the opposite direction of delta x, so here it is 180 degree. Okay. N is perpendicular to Nx, so here it is 90 degree. So it means that the work done by all these forces, that here work done. Here it is P times delta y, here it is minus Fs times delta x, but here it is 0. So it means that total you will get work done as P delta y minus Fs delta x. Now what is the relationship of your delta y and delta x? So what is your x basically? L, this is theta. So L sine theta. It means that x is given by L sine theta. What is y? Y is this, which is just L sine theta. So your delta x will be given by 2L cos theta, delta theta. So delta y is L cos theta, delta theta, and you will find that delta y is nothing but delta x by 2. Okay. Now, so under equilibrium, so what you will get over here, so delta y is nothing but delta x by 2. It means that you have t minus 2 delta x. Okay, so under equilibrium, delta w should be 0. So that gives you Fs is equal to by 2. It means that the spring force is given by 2. Okay. Now, but what is Fs? Fs is nothing but total of x minus h, right? So Fs is equal to P by 2. But Fs is nothing but k times s. What is s? S is x minus h. What is x? X is nothing but here. X is nothing but this particular thing. L sine theta. It means that L sine theta minus h. So using this particular relationship, you can have your sine theta is equals to by 2k plus h. So by 2k plus h, right, and by 2l. So what it will give? It will give you sine theta is equals to p plus 2kh divided by 4kl. How you have to solve and apply the principle of virtual work to get the equilibrium state of any given system under the action of external forces. Now let me finally let me also describe the connection of this virtual work with the principle of and I will so relation of virtual work and potential energy. Now, under the action of conservative forces, what are the conservative forces? Inertial. The weight of a body is a conservative. Friction is not conservative. Okay? So, under the effect of conservative forces, you will see that the work done W is given by minus times the change in potential. Means that here the work done will be given by U1 minus U2. Really, this is U2 minus U1, but work done will be given by U1. Now for the inertial case, the body having weight W, your potential energy is given by W. Okay, so this can also be written as m into g. This is nothing but m g h, and h is the position of the body from the reference plane. Second, if a body is spring, the spring having spring constant K, the potential energy is given by half into K square. X is the extension of the spring. So it means that this is how the potential energy can be written for a given body. Okay? So it says that under equilibrium, your dW should be equals to 0. So it means that your dV should also be less than 0. But what is this dV? This will be dV by dou. Let us say V depends on displacement, which is small u, theta, and all that. So in that case, what will happen? Let us right now assume just one variable. So this is your dou u by the displacement. So dou u by dou small u into dou u equals to 0. So for non-zero, your p by u equals to 0. Since it depends on one parameter, it is similar to saying dv by dv equals to capital U. This will give you the state of equilibrium position. But it's wrong to write state. Just it gives you the equilibrium position. Now to find out the state of equilibrium position, find out d2, right? Now if this one is greater than 0, that potential energy is minimum. It means it is stable. If it is less than 0, then maximum. Potential energy is maximum, and when this becomes 0, that is called inflection point. So we have to analyze the system like further to know what would be the right. This is a neutral position. How you try to find out the state of the system. Now, just I will end this one with a given example of how you have to complete the problem. Let us say you have example which is given like this, and here your spring. Okay, and here you are having mass of one block which is having, you have a block which is having mass m and a spring having spring constant k. That's it. So you will have to find the condition of equilibrium. You can assume that there is your theta. This is your x. So what you have to do is to apply potential energy approach. Okay, potential energy approach. So in this case, you first have to find out the potential energy in the whole system. So you can see that there is a spring which will be having potential energy half kx square, and there will be y which will be having potential mgh. So what is that particular deflection? So let us say, let us fix your axis over here, y, and this is your x. First of all, you will have to find out, let us say x is your displacement. X is your displacement. Potential energy of the whole system will be given by mg. Let us say this is your y. So mgy plus potential energy in this particular thing, since this is half kx square. Now what is x and what is your x is given by, x is given by your, again, L sine theta. So 2 L sine theta. Assume that this is what you're having. And y is equals to L cos theta. You can simply substitute these two parts. So this is your, let's say, V. To find the equilibrium position, what you have to do is dV by d theta equals to 0. dV by d theta, if you find out what will really happen over here, is this will become mg y by d theta become x. Okay. So what is dy by d theta? dy by d theta, dx by d theta is cos theta, and dy by d theta is minus 2L sin theta. Substitute these two values over here, you will have mg 2L sin theta, here k 2L sin theta, and dx by d theta that you are having is L cos theta. Okay, and the variation of this should be 0. So sin theta, if you take common, what will happen? Sin theta you can take common. 4L square cos theta times k minus mg So for sin theta equals to 0, that is not possible because theta is not 0. Cos theta L. So this is what will give you the position of equilibrium. Now to find out whether it is a stable equilibrium, what you have to do is, again you will find out dV by d theta square. Okay, so if it comes out to be greater than 0, you say that energy becomes 0. If it is less than 0, that is maximum, means unstable. If it turns out to be 0, then there is a problem. You can't really say it is stable or unstable. For that, you will have to do further. This the